Walker Gallman, and today I will be covering Lab 5 for Physics 2211 on the topic of a falling slinky. This lab aimed to study and investigate the motion of a falling slinky. The goal was to determine whether the bottom of the slinky remains stationary until the top of the slinky has compressed and meets the bottom, then causing the bottom to move. I used Tracker to observe and track the motion of the bottom of the slinky and used GlowScript to create a computational model predicting the ideal motion. And the results of the lab determined that the bottom of the slinky remained stationary in both the real-world and computational models. However, due to minor fluctuations from external forces, there were slight deviations in the datasets. For fundamental physics principles, I used Newton's second law, which says that the system's momentum change relates directly to the net force applied. Same thing here, the change in momentum over the change in time is equal to the net force. And two update formulas, both derivations from Newton's second law, the velocity update and position update formulas, were used in the computational model to predict the velocity and position of the bottom of the spring, a slinky. The concepts of the force due to drag and the force from the slinky were crucial in this analysis. The force due to drag is as outlined below, with B being equal to the proportionality constant, and V is the speed of the object, with V hat being the direction of the speed of the object. The slinky force is the same concept as tension, which counteracts the force due to gravity, meaning that the slinky force is equal to the tension force, which is equal to the positive force of gravity. I used a short video to track the observed motion. The object had a mass of 0.218 kilograms, and on the tracker software to calibrate the position and the scale of the video, I used Derek's height, the man on the left, to scale the corresponding height and scale of the video, so I could calculate the correct displacement of the slinky. The initial position from the tracker software was at negative 1.11 times 10 to the negative 16th meters in the x direction, and 2.22 times 10 to the negative 16th meters in the positive y direction. And overall, the slinky's initial velocity was 0 meters per second. And as you can see in the graph collected from Tracker, the bottom of the slinky remained stationary until 3.56 seconds, and then it began to fall. Here's the video of the tracking software. Moving on, in the coding phase, I set up these initial values, including the object's mass, setting the object's initial position and velocity, identifying delta t, or the change in time, as 0.01 seconds. Also, I identified two constants used throughout the code: the gravitational force near Earth's surface being 9.8 meters per second squared, and set the value of j hat and set the proportionality constant to 75, which was found via trial and error. The first while loop iterated through each time step, calculating the slinky's theoretical position and velocity, starting with finding the net force, applying it to the update formulas, and then updating time and repeating over and over until time reached 3.56 seconds. However, due to no net force, there was no change in position during the first while loop. During the second while loop, from 3.56 seconds until the end of the motion at 6.16 seconds, there was a net force due to the drag force and weight together combined, which were applied to the update formulas, which then, same thing, they updated position and velocity, iterated through until the while loop was complete. For results, the graph showed the same general trend. The bottom of the slinky remained stationary until 3.56 seconds on both, and then dropped in position. However, there are minor discrepancies in the models, as mentioned before, but said discrepancies are credited in the error section. Potential sources of error include that the real-world system is not isolated from surroundings, meaning there is work being done on the system causing it to perform non-ideally. Furthermore, inaccurate position of the tracker program can be at fault for the deviations in the datasets. Two potential extension questions relevant to this discussion include: why does the bottom of the slinky remain stationary, for number one, and number two, what if we put a large weight at the bottom, would it remain stationary? For the first question, the forces in the y direction cancel out, causing no change in motion. Although the gravitational force acts downward on the slinky acts in a reciprocating force upward like a tension force. For the second question, it would depend based on the magnitude of the weight and the value of the Slinky spring stiffness or constant. If the constant is large enough so that the tension is equal to gravity, then the same ideas from before apply, meaning that the bottom of the Slinky will remain stationary. Thank you.